In this video, I want to continue our discussion of sure estimators in the circumstance when each of the individuals within our system actually has the same independent variables. And what we're hoping to show that is under these circumstances, sure estimators actually collapse to ordinary least squares estimators. So there's no need to estimate the system as a whole. You can just estimate each individual's equation individually. And at the end of the last video, we derived these three results to the right-hand side here, and we were using these as a means to simplify our expression for our sure estimator. And first of all, we were going to look at the product x primed times the inverse of sigma. Well, we know what this is equal to if we just use the expressions on the right-hand side. X primed we just know is equal to in crossed with x bar primed. And then the inverse of sigma we know is just the inverse of omega crossed with it. And I'm using the word crossed here as a shorthand for saying the Kronecker delta product. It's just a bit easier to say. And from our discussion of the properties of Kronecker delta products, when I multiply two Kronecker delta products, this is equivalent to the Kronecker delta product of the first two terms with the matrix product of the last two terms. So the first term is just in times the inverse of omega. And thankfully, because we're doing this correctly, both of these terms have the same dimensions. So this is easily defined, and the identity matrix times any matrix of the correct dimensions is just that original matrix. So the first term is just the inverse of omega. And then the second term in our Kronecker delta product is just going to be x bar primed times the identity matrix it. And thankfully both of these matrices are of dimensions t by t, so this is defined, and this is just going to yield x bar primed because any matrix times the identity is just that original matrix. Okay, so we worked out this product here. Now we need to think about this term within the parenthesis. So if we think about this term in the parenthesis, essentially this is exactly what we've already got, nearly. I mean, this term to the left is exactly what we've got. All we need to do is take that and then multiply it by this solitary x. So that shouldn't be too hard to do. So we can write that x primed times the inverse of sigma times x is equivalent to this result which we just derived above, which is the inverse of omega crossed with x bar primed times x, and x we know from the right hand side is just in crossed with x bar. And then if we use our knowledge of the product of two Kronecker delta products, this is just equivalent to the Kronecker delta product of the first two terms in the respective parenthesis crossed with the last two terms. So this Kronecker delta product just becomes the inverse of omega crossed with, well, the last term is going to be a little bit more complicated. It's just going to be the product of x bar primed with x bar. So we just got x bar primed times x bar. And now we can think about what it would actually be, or what this term would become, if we then take its inverse, which we have up here in the sure estimator. So if we think about the inverse of x primed times the inverse of sigma times x, so I'm taking the inverse of this entire thing, this is equivalent to the inverse of this result which we've just derived above, which is this omega to the power minus 1 times x bar primed times x bar, all inverted. And we know from our knowledge or our discussion of the properties of Kronecker delta products that this is just equivalent to the respective terms inverted. So the first term just becomes omega because the inverse of an inverse is just the original matrix, and then the last term just becomes, I'm just going to leave it in this form, x bar primed times x bar, all inverted. And we're going to use both of these things which we've derived in this video to finally in the next video help us derive the form of the sure estimator when each of the individuals has the same independent variables.